So we present here the results of two related or complementary projects, namely the ProSlide project and the TRANS-ALP project. I will talk about the ProSlide project. So it's a project funded by the province of South Tyrol. And here I will present a data-driven model, which was used for the dynamic prediction of landslide probabilities. So focusing on shallow landslides on the area of South Tyrol. So this first part focuses therefore on the hazard component. And the second part of this presentation will be presented by Piero, and he will focus on an approach to assess and also to visualize potential impact. So this part focuses more on the exposure, on the potential consequences of different kinds of hazards, and it can be combined also with the first part. And in general, we wanted to say that the results and the analysis and the tools we are presenting were designed for large area assessment, which also means they do not replace single slope assessments or field works or something like that. So they were really designed for large areas. Yeah, if we have a look at the literature, we see that the landslide models for large area usually focus either exclusively on the static predisposing factors, so to produce such sort of susceptibility map, which includes topography, material properties, land cover, or exclusively on the dynamic triggering factor. So for instance, intense rainfall events to also produce such rather static, non-spatial rainfall thresholds, which are often used for regional early warning. Quite rarely, those two components, so the spatial components and the dynamic triggering or rainfall components, are integrated. And this is exactly what we tried to do in this project. So we developed a model, a data-driven model that allows us to integrate those static and dynamic landslide controls to predict shallow landslide occurrence at regional scale. And this regional scale is the study area of South Tyrol, so the entire province here. I will not go into detail about the workflow of this study, but just shortly, we start with the observational data. We have, here you see the red points, lots of landslide observations from the last 20 years. And we also analyzed almost 10,000 rainy days without landslides. And we analyzed them in terms of different explanatory variables, so dynamic precipitation layers. So for instance, short-term cumulative precipitation, so this is rather the trigger. Antecedent precipitation, so a proxy for the soil moisture. We included some seasonal effects and also typical variables that relate to landslide predisposition, slope angle, curvature, forest cover, lithology, so some proxies also for the underlying material. And then we linked the landslide occurrence and non-occurrence data with those explanatory variables using a generalized additive model, which roughly said had the task to separate rainy landslide observations from rainy non-landslide observations. And then we transferred our relationship into space, and we also validated the results. So let's jump immediately to the results. What you see here in this graph, in this animation, is are the modeled effect of different kinds of precipitation. So here you see for us, for these daily predictions, short-term precipitation. And here you see the amount of antecedent precipitation on the probability of landslide occurrence. So dark colors high probability, light colors low probability. We also produced some specified thresholds. And what we actually see first is that if it rains a lot, we are in the highest probabilities, and the other way around, we are in the lowest probability as expected. But as you can also see here, day of the year, we also see a seasonal variation of the effect of precipitation on landslide occurrence, which in our case is very likely to be associated to vegetation. So what we see here is in summer, more precipitation is required to trigger a landslide compared to winter. We have in summer, we have vegetation is working, evaporation, transpiration, and so on. And this might substantially affect also this seasonal variation of the effect of precipitation on landslide occurrence. We can also compare the precipitation effect with other spatial variables. So here you see again short-term precipitation, and here different kinds of spatial variables. Here again, landslide probability in the dark color, it's high, and here it is low. And what we see here is if there is a heavy rainfall event, so have a look at this red line, so 100 millimeters in 2 days, which is not always heavy, but in this context, it's a heavy rainfall event. Landslides occur more likely at medium inclined terrain. So the terrain must not be too flat, obviously, but also not too steep where no soil cover is available. At relative lower slope positions where we might find deeper soils and more water accumulated from upslope areas. And also in usually drier areas. So for instance, in South Tyrol, this is the western part, and the drier areas that experience or are less used to wet conditions compared to areas that are quite adjusted to those wet conditions. So this is also a factor. And also landslides occur more likely at outside forested terrain. So also here, of course, forest plays a role. What we can then do is we can transfer all these relationships and others in a model into space to do some hint casting, which means we run our model for a past event to verify our model and to produce such sort of dynamic maps or with different thresholds. So roughly said here in these darker colors, blue and purple, we have more the typical landslide conditions. And in these light colors, we have the untypical landslide conditions. Then you can see here example for a heavy rainfall event that occurred on 4th and 5th of August 2016 in the Pasaya Valley. So here you have two kinds of precipitation variables, short-term precipitation, medium-term precipitation before this short-term precipitation. And here you actually see the model response. So here they zoom into that, and what you can actually see, we got here also the model predicted the highest landslide probabilities exactly during this heavy rain event, and all observed landslides. So they pop up on the 5th of August. So now highest probabilities, and these points are the landslides. They all occurred within the highest two probability classes. So in this case, yeah, it seems to work well. In the last few days, we also tried to do some hint casting for the VIA precipitation variables in terms of landsliding. What you can see here just in this, again, in these rainfall variables, that yeah, the period or the October was relatively dry until 23rd of October, and the heavy rain started around the 27th of October. And here we can see again our response model or the model response. And we see that actually most landslides in this area occurred on 28th and 29th of October, and almost all of them occurred in areas within the highest probability class or in the last threshold. So here. Finally, besides hint casting, with this model, we can also play with scenarios. So we call them narrative scenario, which means we simply add, instead of past rainfall events, we add hypothetical precipitation amounts to our model. And then we can play with different kinds of scenarios. So here in this example, we simply add this short-term precipitation variable. So we add 5 millimeters for a rather dry antecedent conditions scenario and see how the probabilities change. And here the scenario 2, we also add this short-term precipitation. And here we are playing with a rather wet antecedent conditions, also to see more or less how the response of the model is in this context. What we did not do yet, but might be a future step, is to move towards nowcasting using also radar data, or even, yeah, let's see, even trying some forecasting by feeding our model with data from weather now or forecasts. And with this, I leave the floor to Piero that focuses now on the exposure part.
Yeah, thank you, Stefan. Hi, everyone. Okay, so yeah, exposure. This is so within the frame of the TRANS-ALP project, a first effort that we did, thank you, Catherine, is to collect that data of exposure from the both Italian and Austrian territories and try to harmonize them. So here is a sample of them. We have more of that. So we have roads networks, human settlements, land use, and all sort of vulnerable hotspots like schools and hospitals. And what we did is to put them all, harmonize them all together onto a same spatial support. You can see here these beehive-like hexagons. So we opted for these hexagons because they're usually topologically better than just plain squares. You know, this is what we are trying to model, not just aggregation of data, but also the connection among them. So we have roads, but we might have also, I don't know, power grids and water conducts. So this was the model that we chose. And yeah, that's the first task that we will show. I will show this later on in real time. And second part is, again, in the TRANS-ALP project, predicting the dynamic population flow. So this is a set of input data that we had from the local province of Bolzano. So we have, you see the employees data, the resident population, and the weird thing on the right is the point-to-point trip information of home work commuters every day in the pre-COVID, was I think 2018. So we had these data sets and we wanted to reach this point. So again, on these, those are hexagons. Again, it's just the same spatial support as I showed before. So we wanted to have a sort of multi-temporal intraday view assessment of the population. So we have the usual nighttime static population, we have the daytime expectation, and then we also have there on the right, like the assessment of the commuting population. So during commuting time, where is the population? So this is an effort to have a more accurate view of where is the population, which is the most important exposure asset. And yeah, this is just to show that we could also, I mean, combine these pieces of information into multiple layers. So maybe you want to see the daytime population overlaid with the commuters. So this is, we played a bit with this. And the last slide, then I will jump into a live demo. This is just a preview of maybe a panel for discussion with the civil protection or whoever's interested on a potential web tool for forecasting of impact and maybe operational early warning assessment. So this is, for example, on the right, you see we might feed this web GIS with the exposure data I showed you now and the landslides, susceptibility maps that Stefan showed also, climate extremes identification and whatever else we have, and then put them in this map and then have some kind of useful tool for operational early warning and risk management and reduction. So let me just quickly click on this link. See if it works. See. Okay, I think I should turn off this. Anyone knows how to get out of the presentation here? Yeah. This is, I found it now, and slideshow. Yeah, okay. Thank you. Okay, this is the link. This is the map I prepared. So first of all, just to let you understand, this is the, you see above maps, Eurac edu. This is just a simple agnostic library of geospatial data set. It has some basic tools for creating maps and playing with them. So this is just a very general purpose. It is not tuned to risk assessment or management, but that's might be a place where to discuss and talk about possible functionalities that might be nice to have. So, okay. So you see, first of all, let's just, here we are in Bolton. This is our study area, which comprises South Tyrol, Argordino Valley, and East Tyrol. And this, if we zoom in, you see this is the hexagonal tessellation common ground I was talking about. So this is our analysis of support of analysis. And so now I'm going to show you a bit the data set that we've been producing for the TRANS-ALP project. Let's have a look. So here, for example, this is the harmonized tessellated exposed assets. So here, throughout the transnational area, we have all sorts of information I'm going to show you now. We can have, so this is what we're showing here is the buildings area, for example. We have protection forests. We can have the artificial surfaces, so they're all like aggregated together in the same spatial support. And then we have as well this is the dynamic population data that also was talking to you about. So we can have the daytime or nighttime or commuting time. And I'll just, sorry, this one. So we can view, this is, for example, now the commuting time population. We can switch to the nighttime or the daytime. And let's go further. We have also information on the roads. So for example, this is, this is an interesting data that we computed, is the accessibility to the nearest hospital. So this gives you also kind of vulnerability information. So the more, the darker, the more you need an helicopter rather than, and so it's also useful to overlay that as additional information, maybe with, for example, roads information. This is OpenStreetMap roads data sets. This is just the thicker the main roads goes to motorways or. And another example of roads information we've been computing is this one in red. It's just a topological indicator of how critical a road might be. So just analyzing the critograph of roads tries to hotspot the most critical roads in the graph. And what we have here also, we have, this is the projection of the homework commuters on roads. So this is another information that can be visualized on top of it. And then as a final thing, examples, so talking about the VIA event, we can also overlay the susceptibility, the probability of landslide map on top of it. We also have the EFI and flood events data set. So you can see here below, we have a time slider and we are on the 26th of October, 2018. So like to maybe civil protection, like imagine you have such a tool 1 week before the VIA event that can give you forecast on possible impacts of the storm. What would you like to have? So just go on as 27, you see here in purple, there is more probability going on. And then on the 28th, you see it, this is getting worse. The first landslides from the EFI datasets are popping up. And then on the 29th, it's getting even worse. And then the storm is gone. I think it's overdue now with time. Any questions we're glad to answer? Thank you very much. Okay, yes. Yeah.
Thank you very much, Stefan and Piero. That very much work in progress, but we wanted anyway to give you a hint of what can be done with this type of tools, especially when we take different projects and put those results together. Is there any question?
Very interesting compliments. Can we switch to the map again and to the road sign?
The roads, yeah.
Yes, the roads. I just wondered, I think that the Mabo and the, is this the road one? How critical
Yeah.
the road is? Oh,
The,
then I've
No.
seen wrongly first.
this is
Sorry.
the,
This is.
the,
On which factors was the critical
Mm-hmm.
thing assessed? Sorry.
yeah, was just a purely topological analysis, just we see the whole network of roads as just a graph, so no further information, just topological. So that there are indicators, there are just well-known one which analyzes, like they simulate having a trip from each node of the graph to each other node of the graph.
Yes.
So they make all different possibilities, they run it, and then, a road which is transited
to
more
be
times is-
engaged in a traffic jam, or to be engaged in that the road is
it's more likely to be routed by people. So like if you would see like the Manhattan plan, you will not have very like critical points because it's very distributed. So if one road gets
I was
interrupted,
just wondering why the road is going through the Drususallee and not through the Mabo and the
Sorry.
junctions, the junction on the Autostrada.
I didn't, sorry, understand.
I was
You-
just wondering why the red road sign. So if you switch the map,
the red one, yeah.
yeah, is
This one,
going through
Mabo,
the
yeah.
town and through the town. Yes, no, in Bozen.
Here, Merano,
Bolzano.
Bolzano, sorry, okay, yes.
Why it is going through the Drususallee and not through the Mabo Sud and the
Like
others?
doesn't like it's why it's not more critical.
Yes,
here.
I was just wondering that.
Oh, that's this is again purely topological. So it doesn't even know about kinds of roads, if it's secondary or primary.
It doesn't know that.
No, it was just
Okay.
like all roads. Yeah,
Okay.
just a
Okay,
prototype.
thank you.
Yeah. Short distance, exactly, yes. But it can be refined, yes. I mean, it was actually, the algorithm was weighted a bit by the road types. So like a motorway would be anyway chosen, even if it was a bit longer. But yeah, so there is a kind of weighting regarding the types of road, but yeah, then it's
But I think this is not entirely, let's say, incorrect, because this takes into account all the roads in the network, and basically the reddish is the road, and the more critical will be the transportation on the network if this road will be interrupted, so to say. And as a matter of fact, it seems that from the topological perspective, the road which is used to traverse the town is more critical, especially for the people which are using the town itself. So it doesn't matter whether, of course, if you want to go somewhere else outside the town, this would be different. So on a specific trip based, the criticality would be different. But on a topological perspective, the town needs this type of let's say end-to-end roads that would allow people to go from one side to the other. So we didn't go too much into the details of the modeling because probably we are missing some information starting from OpenStreetMap. So maybe we don't have, let's say, consistent information on the capacity of roads and so on. But I think the tool is actually quite interesting because really out of the box gives you, let's say, a lot of hints about which roads might be more critical in case they get interrupted by a landslide, for instance, or other disruptions. So,
And yes, and also the weighting scheme, like which weight to assign to a primary road or to a secondary road, to a tertiary road, was like arbitrary. So that also contributes to the outcome. So maybe tuning a bit these coefficients would change the picture, but we didn't go on further on the study. Yes.
looking forward
Thanks.
to have your comments on this and feedback, by the way, because this could be useful. Thank you again. All of this is available to all the partners and stakeholders of the projects. So if you want to play yourself with the interface and the platform, just let us know.